Okay, thank you, and good morning, everyone. And thank you very much for having me on this Saturday morning to present my recent work on Bianchi cosmologies with massless Vlasov matter, which is available on Web and it is going to appear soon in CQG. So let me start right away with the motivation. I'm interested in mathematical cosmology, and one of the main goals of the mathematical cosmology is to understand and determine the future fate of the cosmological models. And by cosmological models, I mean the model that consists of three essential elements: cosmological model, cosmological spacetime, theory of gravity, and matter model. So in this talk, I'm going to consider Bianchi spacetime, which is a subclass of spatially homogeneous spacetimes. I consider general relativity with vanishing cosmological constant, and I take loss of matter as matter model. So why I do that? Because there are some observational challenges in the concordance model of cosmology, which suggests that we may abandon the assumption of isotropy. On the other hand, I'm interested in Vlasov matter, which is a reasonable matter for describing the stars, galaxies, or even cluster of galaxies on larger scales. It models the matter, and it assumes that the matter doesn't have collisions, so it's reasonable. And on the other hand, I'm interested in the vanishing cosmological constant case, because as it pointed out by Zoe 2 days ago, things are less better in the case where cosmological constant is present. So then show the future attractor of the massless Einstein-Vlasov system for Bianchi types 2 and 5. In the Bianchi cosmologies, the Einstein equations reduce to ODEs, but the Vlasov equation remains a PD in general. If one assumes forward symmetry, then, for example, the locally rotational symmetry, abbreviated by LRS, then future attractors could be found by dynamical system approach globally. And there are lots of work in this direction with perfect fluid. And for example, the classic textbook on this subject by Ellison Wainwright. But also there are some works with Vlasov matter initiated by Randall and Todd in 1990. But otherwise, one has to assume small initial data if one doesn't want to assume forward symmetry assumption. But nevertheless, one can determine the decay rates with this approach. There are some results with massive Vlasov matter on Bianchi type 1, 2, 7, and 6, 0 by Nungesser, and Bianchi type 5 by Anderson and Nungesser. So the massless case is more challenging because we have a slower decay rate in the course of the expansion of the universe. So my proof is a little bit different. I used energy method and Bootstrap Agreement, which go most of the time hand in hand. So Bianchi spacetime is a four-dimensional Lorentzian spacetime, which is globally hyperbolic and could be written as a warp product of an interval and a three-dimensional simply connected Lie group, which admits a left invariant frame, which satisfies the commutation relations where Ci, J, K are structure constants. And by choosing the appropriate frame, the left invariant frame and its dual are time independent, then one can write down the Lorentzian metric in this form where Gij is Riemannian metric and it's time dependent. So the important properties is that one can classify Bianchi models by classifying the structure constants of the Lie algebra, which could be written uniquely in the given form, where epsilon is the Levi-Civita symbol and n is the symmetric constant metrics, and ai are constant. So by a unimodular transformation, this constant matrix n could be diagonalized, and we have the three eigenvalues n hat 1, 2, and 3. So therefore, Bianchi class So Bianchi models could be classified into two classes, A and B, in terms of the constant A. And in Bianchi class A, we have these different types, 1, 2, and so on. And in Bianchi class B, we have Bianchi type 5 and 6H and so on. So I'm considering Bianchi type 2 and 5. And you see the eigenvalues of this matrix n. In Bianchi type 2, the only non-vanishing constant is n1, and these eigenvalues could be normalized to 1. I'm going to make a remark on Bianchi type 1. And on the right-hand side, you see different spaces. There are 7 spaces, and there is also another space S2 cross Euclidean, which corresponds to Kontowski-Sachs model. So as you already noticed, these are 8 different geometries in Thorsten's classification. So let me make a final remark on Bianchi. It is usually assumed in mathematical cosmologies that the spacetime should admit compact Cauchy surface. If so, then the only Bianchi types 1 and type 9 admit compact Cauchy surface. We therefore usually consider locally spatially homogeneous spacetime. However, this doesn't enter my calculations. Otherwise, there is no need to prove the stability of Bianchi type 5 because of the most of rigidity theorem, which says that 2 compact hyperbolic spaces are isometric up to global scaling factor if they are homomorphic. So let me introduce the Vlasov method. Fortunately, Leo introduced this yesterday. This method modeled the collisionless kinetic gas, and they are modeled by a distribution function f, which is defined on the mass shell, and in this case, the mass is 0. So to this distribution function, one can associate an energy momentum tensor, which is given there. So the important assumptions here is that F inherits, so to speak, the symmetries of a spacetime, and has therefore the particular type on the right button. The second assumption is that I assume that F has compact support. And then energy density, energy current, and spatial part of the energy momentum tensor are given by these formulas. The point is that the trace of S is equal to energy density. And finally, the transport equation or Vlasov equation or collisionless Boltzmann equation is given by this formula, where gamma bar is the connection coefficients with respect to the Lorentzian metric in the left invariant ray. So then Einstein-Vlasov takes the following form. The first equation is the Hamiltonian constraint. The second and third one are evolution equations for trace part and trace-free part of the second fundamental form. And the fourth equation is the Vlasov equation, where omega ij are Ricci rotation coefficients. So h here is Hubble parameter, which is minus 1/3 of trace of the second fundamental form is positive because the universe is initially expanding, as we assume. And we define the Hubble normalized parameter by capital sigma, where sigma is the trace-free part of the second fundamental form. And then we define for the Hubble normalized parameter, the sigma plus minus. So omega is density parameter, Q is the deceleration parameter, and I also introduce the normalized, Hubble normalized Ricci tensor. So to this Einstein equation, one should couple the evolution equation for the curvature term, which is connected to the constants of the Bianchi types. So in the first attractor, I call generalized Collins-Stewart solution, and it's observed that in Bianchi type 2 by Keller and Hasler, that in Bianchi type 2, with LRS assumption, massless collisionless particles have the future attractor, and it's anisotropic. So we have the dynamical variables. So this N1 here, it corresponds to the curvature, and it corresponds to the non-vanishing eigenvalue of an N. So for the proof, I had to assume the reflection symmetry. It corresponds to the diagonality assumption by assuming that the distribution function initially has the following symmetry, and first and second fundamental form are diagonal, then the energy momentum tensor are diagonal, and so this symmetry is preserved by the evolution of by the evolution equations for all time. And the second attractor is the mill universe, as we have seen this already. It's a class of FLRW model with negatively curved spacetime, spatial part, and with vanishing energy density. So in the left invariant frame, we have this particular form of the metric, and the variables, dynamical variables, are these following. So as we have seen in the talk by Zoe, this universe is non-accelerating or non-decelerating. So let me quickly say the theorem considers a smooth solution, initial data G sigma F for the massless Einstein Vlasov system with reflection symmetry, Bianchi type 2 symmetry. Then if we assume that this value sigma plus minus 1/5 and so on, they are small, that is, we are a little bit away from the GCS solutions, then we could show the following estimates, and we show that this model is not only stable but also asymptotically stable, and corresponding result for Bianchi type 5 is the same, where I don't assume the LRS, and I show this generally with this estimate rates. So the proof is based on Bootstrap Agreement. So because we assume that these values are initially small, we could assume that on a small interval t, not in capital T, we have the following decay rates. And if one could show that, or if one could improve these bootstrap assumptions, meaning that if one could show that they have faster decay rates, then by continuation criterion, one could show that capital T is infinity. So I do this by shifting the system and linearizing the system around the attractors, by the shifted parameters denoted by hats. So the last equation here is the evolution equation for the curvature, and I highlighted, so we have the corresponding result also for Bianchi type 5. I highlighted the bad terms, the critical terms, energy momentum tensors. So the essential proposition of the work is to estimate, to get good estimate for these energy momentum tensors. And we follow two different strategies. First, we look at the evolution equation of the energy momentum tensor, where the Vlasov equation enters directly, and we see that we have the bad term Yij, but if we assume reflection symmetry in the particular type of Bianchi 2, this term vanishes and one can show the results. On the other hand, for the Bianchi 5 type 5, we take advantage of the characteristic curve of the Vlasov equation, and one could show that the momentas are asymptotically constant. And since the distribution function has initially compact support, one could go to an spatial orthonormal frame and show that the energy density decays as t to the -4, because distribution function is constant along the characteristic. So then we define energy functions. Simple, they are simple, and in terms of the perturbed variables, and by introducing two constants C1, C2, or D1 and D2 in different types, and then one eventually shows that they decays, and the square root of this decays gives the estimates of the theorem. And so I think I'm already running over time. So let me just mention that with the same method, we showed in a joint work with David Feynman and Gernot Heissel the isotropization of the slowly expanding spacetime. And let me also say that this method couldn't work for Bianchi type 7, although they are almost, I mean, one expects that it should work because it corresponds to Sol geometry, and Bianchi type 2 corresponds to new geometry. But I wasn't fortunate to show that. So I leave you with this last slide, and thank you very much for your attention.
I'm muted. Thank you very much. I will clap for everyone. So we have some time for questions.
So, Kamet, can you explain again why you're using Bianchi 2 and 5? Why not the other ones? Maybe you explained this, but I just missed the point.
No, I mean, the other Bianchi types are, I mean, for the massless case, there are, in this approach, I know just one work which we did and another group. And so Bianchi type 5 is the easiest case in class B, and the easiest case in Bianchi type A after type 1 is the type 2. So that was the reason, because they are easier.
Okay, but so the equations become more complicated. That's the point. If you allow the
I think the point. I'm sorry. The point is that so these components of the energy momentum tensor, they are too critical. For example, in type 6.0, I wasn't fortunate to get a good decay rates for them. So this.
So you've tried the other models and they just don't work well. That's the problem. There are technical difficulties.
Yeah, exactly. So 6.0.
And similarly for this symmetry hypothesis, if you drop this symmetry hypothesis so that you get some currents, then you're in trouble. Is it?
Exactly, for the Bianchi type 2, exactly. So Bianchi type 2 was also critical if you drop the LRS, so locally rotational symmetry.
And as usual, this is only to the future, right? So who knows what happens for small t?
So you mean past direction?
Yeah, right.
I think it's very complicated, but
Yeah.
I guess in Bianchi type 5 it's easier. It should be Cosma, I think, and for Bianchi type 2, I think it should be Tau, if I'm not mistaken. But I was concentrated in
Sure. Yeah. Okay. Just thank you.
Okay. Thank you.
May I ask a general question? In this book by Ellis and Wainwright, they treat the Bianchi models as dynamical systems, as you did, and there are a number of flow pictures towards the attractors and so on. Is that possible for what you have been doing? How the attractors are approached in the space of the dynamical variables?
So as I said, they approach the attractors in infinite times. So I'm not using the dynamical system approach. For dynamical system approach, as I said, you have to assume 4 the symmetries. For example, LRS, or I mean, they assume more symmetries, particular form of the distribution function and so on, because otherwise the dimension of the variable space is very large, and one cannot do the dynamical system.
May I ask on what you display now? This the G, the diagonal,
Yes.
with this exponents of t, is that correct? Is not
Yes.
one of them at least negative? Is it
No,
2/3, 4/3, 4/3? At least,
no,
at least in the Bianchi 9, and sorry, in the Bianchi 1.
Yes.
There should be one exponent be negative.
I think you're thinking of Cosma models.
Yeah, that's
First,
right.
Yeah, but the metric is Riemannian. It could be, and it's a covariant version of the metric. So the Gij down. So it could be, it couldn't be minus. I mean, the publish couldn't be minus.
Mm-hmm. Mm-hmm.
So the inverse is the minus 2/3, minus 1/4, and so on. And
I think Peter's point was that this is not a Bianchi. Yeah, Bianchi one would have different exponents than this one, right?
Yeah,
So
exactly.
but
that's Bianchi too, right?
Yeah, there's Bianchi too. So
yeah.
Uh-huh.
And it's the future attractor. So in Bianchi type point, the future attractor is isotropic.
So that then all direction expanding, yeah, all direction
Expand
expanding.
and with different rates.
Yeah. Mm-hmm.
In general.
Okay, thank you for discussion. I think I don't see any questions in Q&A or in the chat. So let's thank Hamid again. Thank you very much. And we move on